So we've been looking at intermolecular forces and how our different particles start to affect one another. As these forces of attraction become greater, there's more attraction between our particles. We end up seeing different properties based upon kind of these attractions. Ionic solids. If we think about our kind of ionic crystal, the fact that we have this very rigid, brittle solid at room temperatures, the fact that we have these high attractions from fully charged particles next to other fully charged particles. And this is where we get kind of this ionic crystal. Just one of those pieces to think about. As a reminder, when we say an ionic solid, this is an electrostatic force that holds our cations and our anions together. The strength of this force changes with the radius and the charge. We talked about this quite a bit in college chem. There's kind of two factors when we talk about ionic strength. It's the size of the ion and the charge of the ion. I'm going to show Coulomb's law for just a second, but hopefully it kind of brings to light why we see this trend that we do. So Coulomb's law, don't worry about the formula here. It's just meant to kind of show the mathematics of it. We said the force of this attraction is related to the charges of the cation and the anion multiplied together, so those are the Q's, divided by the distance between the radius squared. Well, what does this mean? Well, if the charge is greater on our ions, the numerator increases, and that value when calculated is greater. So a 1 plus 1 minus charge is going to have less attraction than a 2 plus 2 minus charge. Oh, okay. The denominator piece here, the radius. What this means is as the ions get larger and they're further apart from one another, well, that's in the denominator. We're dividing by a larger value. The charge would then, or the force of attraction would decrease. And so it's kind of this push-pull. But basically, at the end of the day, the greater the charge and the smaller the particles, the stronger that ionic solid is going to be held together. And we actually see this in the data. So if we compare two compounds, two crystals, our sodium chloride and our magnesium oxide, if we're thinking about the size of these particles, we've got our sodium and our chlorine, 1 plus 1 minus, and we've got a larger size on the sodium and the chloride. Our magnesium and our oxygen are both going to be smaller, and they have a 2 plus 2 minus charge. That's why it takes so much more energy at a factor of 2,000 more degrees Celsius to get it to melt. That's MP is melting point. It takes more energy to melt the magnesium oxide than the sodium chloride because it's got a greater charge and the ions are closer to each other. Again, just kind of nice to think about what this means for us when we think about our solids and these ionic charges. Cool, just generally speaking, it's because of these charges and the dipole nature of water as to why many ionic solids dissolve into solution. If you've got these polar molecules of water that have a partial positive and a partial negative, well, they're going to crowd around these ions and pull them apart. That was our ion dipole force. Generally speaking, most ionic compounds become more soluble as heat is added. That's not always the case, but as a general rule, is pretty safe to say. Just a reminder, some ions are either so strongly attracted to one another or are so large that they do not dissolve into solution, and that's where our NAG-SAG, PMS, Castro-Bear solubility rules come in. Now, obviously, we've kind of tried to make this black and white. There's always going to be some exceptions, and there's going to be kind of a gray area. We'll talk more about solubility when we get to a little bit later on in chapter 19. Cool. Come back to this likes dissolves like idea. So if we're thinking about, so we're done talking about ionic, let's talk about molecular. Molecular would be our covalent compounds. Typically, these are substances that are non-polar or sometimes polar, but are covalently bonded. When we say molecular, we're saying that they are covalently bonded atoms or molecules. And so these would be all nonmetals. If we're looking at kind of our structures here, we're looking at methanol, ethanol, propanol, butanol, pentanol, hexanol. That all ending means it's an alcohol. That just means the functional group is an OH. We'll talk more about organic towards the end of the year. But you'll notice that all of these end with a little hydroxyl group, which means they're all going to have hydrogen bonding. All of these are slightly polar molecules. They've all got hydrogen bonding occurring because they've got a hydrogen bonded directly to an oxygen. So methanol, for example, is very much a polar substance. If we try to dissolve it into water, which is also polar, it always dissolves completely into water. But hexane would be C6H14, whole straight chain alkane, non-polar as nature. The only intermolecular force would be LDF, or London dispersion forces. You'll notice that it does not dissolve particularly well, only 1.2 moles per kilogram of hexane. And you'll notice as we start to increase the length of the chain, our solubility actually changes. So here on our second one, ethanol, we've got a CH3 and a CH2. Well, that CH3, CH2 end is non-polar. Just the end with the hydroxyl group is polar. Because it still has that polar end, it's still soluble in water, but now because it also has that non-polar end, it also dissolves in the non-polar hexane. Oh, if we look all the way down here at this last example, this hexanol, we've got this super long non-polar chain with just this little bitty hexanol alcohol group at the end, the polar end. It still dissolves into water, but very, very poorly. As we increase the non-polar end of the molecule, it becomes less and less soluble in the polar water. And we can see this with all sorts of stuff. Your oils, we know, don't mix with water. These are immiscible, they don't mix. The reason that is because you've got your polar water and your non-polar oil, and they do not mix, as the old saying, don't mix, oil and water don't mix. Cool. Couple of other pieces to kind of talk about. I'm practicing ionics. If you're interested, you can be working on that. When we talk about solubility, when we say something is soluble, to what extent? There's some pieces in here about rate of dissolving versus recrystallization, but really just in its basal form, if something is undersaturated, that means you've added a little bit of a solute. Remember, solute is the thing that gets diluted. The particles we're putting into solution. The solvent does the dissolving. So if it's undersaturated, that means we have room to add more particles into the solution. If it is saturated, we say we've put in all of the solute that we can, and no more will dissolve. And if it's super saturated, that means that we've got too much. Typically, that means we heated it up, we dissolved a bunch of stuff, and then we cooled it back down. And if we put a seed crystal in, we actually get it to crystallize back out. Sometimes we say oversaturated. If something is oversaturated, that means there's too much in solution, and things will start to settle out as a precipitate, or things will come out of the solution. That's kind of the three basic types of ways in which we describe solutions, either undersaturated, saturated, or supersaturated, oversaturated in nature. Cool, just want to talk a little bit about some more of these intermolecular forces and kind of these kind of exceptions or detailed pieces. We'll kind of carry on looking at these intermolecular forces and how they start to affect what we call our colligative properties.